All right, welcome back to another calculus lecture. In today's video, we are going to introduce rules for computing the derivative, which allow us to circumvent having to do a limit computation every time we want to do a derivative. In practice, this really is not feasible, so we would like some general rules that allow us to compute derivatives quickly. Before we get to the rules that we want to introduce, I want to introduce a little bit of notation. So notation, and this just makes writing derivative rules easier. So the symbols d, dx, so this is kind of like the Leibniz notation, but I don't have a y next to my d in the numerator here. So d dx of f of x, this equals f of x. All this means is that you can think of d dx as an operator, so it's telling you to compute the derivative of f of x. So this just means compute the derivative of f of x. So as an example of this, so last time we saw that the derivative of a linear function is just the slope of the line. So d dx of mx plus b is equal to m. So all this is shorthand for is saying if I have a function and then I want to compute the derivative of that function, I slap a d dx with some braces around it, square braces, parentheses, whatever you want to use, and then just it's telling you to compute the derivative. So that's all that notation means. So the first thing that I want to talk about, so let's write down derivative rules, and there are quite a lot of these. So one, the first thing is that the derivative is linear. I almost just said the twice. Golly. The derivative is linear. That is, so what does it mean that the derivative is linear? The derivative operator, this thing which tells you to perform an operation on a function, this operator is linear, means that if c is a real number and f of x and g of x are differentiable, so I can actually compute their derivative, then if I tell you to compute the derivative of c times f of x plus g of x, and I could have put another constant in front of g of x, like c times f of x plus d times g of x. It would be the same thing here. Or not exactly the same, but you'll see what I mean. The derivative of this thing, the derivative splits apart over the sum, and then the constant comes out front of the derivative operator. So this is equal to c times the derivative of f of x plus the derivative of g of x. And if I had had a constant in front of the g of x, there would be a constant now in front of this derivative operator. So again, all we're saying is that if we want to compute the derivative of a sum, and perhaps with a numerical scaling in front, then it suffices to just compute the derivative of each of the individual functions and split up the derivative this way. And we'll do some examples later on showing how this actually happens. Okay, so the derivative is linear. So let's summarize some derivatives from last time. So the derivative of a constant, recall that the constant is not changing with respect to the variable x. and so its derivative is 0, and the derivative of a linear function is its slope. Because here it is precisely just the rate of change of the line. Okay, so those are the most basic ones. Now let's get into some more interesting rules. So the first one is the first interesting rule is the power rule. So for any real number a, which is not equal to 0, so a is going to be a power of x, and x to the power of 0 is just 1, so we exclude a equals 0. So for any real number a which is non-zero, the derivative of x to the a is equal to, so how do we compute this? We take the exponent down in front as a scalar, we write x, and then we subtract 1 from the exponent. So if I want to compute the derivative of a power, all I do, subtract 1 from the exponent, and then that old exponent now moves down in front as a scalar. From some previous examples, you might have noticed that the derivative of x squared is 2x, and this is precisely what happens in general, is you move that exponent down and then you subtract 1. Okay, so that's the power rule. Now let's talk about the derivative of the trigonometric functions, so trig functions. And here I'll just make a little list off to the side. So the derivative of sine of x is equal to cosine of x. So sine just turns into cosine. The derivative of cosine of x, as you might expect, it turns back into sine of x, but we accrue a negative sign. The derivative of tangent of x, this is equal to secant squared of x. Actually, I should put parentheses around this just to be consistent. And secant squared of x just means the secant of x quantity squared. It's just sort of shorthand notation to put the exponent right here. But secant squared of x, secant, recall, is 1 over cosine. So these are the derivatives of the usual trig functions, and now we can compute the, we can also write down the derivatives of the other trig functions. So the derivative of secant of x, always got to be careful when you write secant of x or else you'll make people giggle. This is going to be secant of x times tangent of x. The derivative of cosecant of x, so cosecant of x is 1 over sine of x. The derivative of cosecant of x is negative. It's sort of similar to what happens with the difference between sine and cosine. It's negative cosecant of x cotangent of x. And remember, tangent of x is just sine of x over cosine of x. Cotangent of x is just the reciprocal of that. It's cosine divided by sine. All right, and lastly, the derivative of cotangent of x is equal to negative cosecant squared of x. And these are the derivatives of all the trig functions. We're not going to prove any of these, although I may add it as a bonus question to maybe prove this one in your written homework. All right, so the next kind of function I want to differentiate is the exponential functions. So if a is greater than 0, so we're only going to differentiate when our base is a positive number. So if a is greater than 0, then the derivative of a to the power of x. So this is kind of like an x to the power of something, but you've reversed them. So now x is up in the exponent. This is equal to the natural log of a times a to the x. So it pretty much stays the same, except that you pick up this factor of the natural log of a. And in particular, we have that the derivative of e to the x, so e is the base of the natural logarithm here, so a natural log of e to the x is just x. They're inverse functions of one another. And so the natural log of e is just 1. The derivative of e to the x is just e to the x. It is its own derivative. And if we have time at the end of this video, if it doesn't drag on too long, then I'll kind of talk about why e to the x is its own derivative. It's kind of cute to see why that's true. Actually, I may just do another video. We'll do a bonus video. Completely optional to watch, but if you're interested, I'll do a video and talk about it. Okay, so those are exponential functions, and then finally, logarithmic functions. So, yeah, again, if b is greater than 0, then the derivative, I'm going to put this on a new line, the derivative of log base b of x, this is equal to 1 over x log b. And in particular, we have that the derivative of the natural log of x is equal to 1 over x. We won't use this too often for general bases b, but we will make use of the natural log of x and its derivative being 1 over x. This is definitely the case that we want to make sure we know. Okay, so those are the derivatives of familiar functions. So now what I want to do is actually just run through some example computation. So if I give you a function and I ask you to compute its derivative, how do you do that? So examples. So compute the following derivatives. And we'll just write down a few examples. So let's say we'll just do the derivative of, I don't know, 3x squared plus cosine of x. Okay, so recall the derivative is linear, so it suffices to just compute the derivative of x squared and the derivative of cosine of x, and then reassemble them using the linearity. So this is going to be 3 times the derivative of x squared plus the derivative of cosine of x, and this is equal to 3. The derivative of x squared, we apply the power rule. So this is the derivative of x squared. I subtract 1 from the exponent, and I move the 2 down in front, so I get 2x, and then plus cosine, not cosine, negative sine of x. And so this is 6x minus sine of x. Okay, so that's a pretty simple example. Let's do another one. So let's compute the derivative of, and now what I want to do is we're going to do x to the power of pi, where pi is the 3.14. It's the ratio of the diameter of a circle to its circumference. So x to the power of pi plus 2, something like that. Okay. Well, if I want to compute this derivative, again, I use the linearity, so this is going to be the derivative of x to the pi. And I do realize that things are a little squashed, especially when writing these dx's. If I had a whiteboard, it would be much better, but alas, this is the format that we have. And then plus the derivative of 2. And now I just apply the derivative rules that I had before. So the derivative of x to a power, this power is non-zero, and so I just subtract 1 from the exponent, and I move this exponent down. So this is going to be pi x to the pi minus 1. Pi minus 1 is a number. It's 2.1415, however many decimal places of pi you know. But it's certainly still valid as an exponent. And then the derivative of 2 is just 0. Again, it's 2 does not change with respect to the variable x. And so this is just going to be pi x to the pi minus 1. All that to say that when you compute derivatives of functions with powers, the power doesn't have to be an integer. It could be a fraction, it could be a negative number, it could be an irrational number, but the power rule applies nonetheless. Okay, maybe let's do one more, just for good measure. Let's compute the derivative of 5 to the power of x plus 7 times the natural log of x. Okay, again, we use the linearity of the derivative. And you don't have to write down this step. We're not going to be like limits and write down every step along the way in the future, but at least for these examples, I wanted to just be clear about every step that I'm taking. If you compute these in your written homework, I'm not going to require you to show me every single step of the differentiation process, unless I explicitly state so. But if I don't, then you can just compute the derivative as you like. So the derivative of 5 to the power of x, and then plus 7 times the derivative of the natural log of x. And here the 7 has come out front because it's a constant. So the derivative of 5 to the power of x, I apply my logarithmic derivative. So I'm going to, or I'm sorry, my exponential derivative. So I get the natural log of 5 times 5 to the x. And then plus 7. The derivative of natural log of x is 1 over x, so I get 7 divided by x. 7 times 1 over x is just the same thing as 7 divided by x. And in terms of how much simplification you should do in derivatives, it's a matter of what is computationally convenient and what are you trying to see with the derivative. Sometimes it's beneficial to simplify them. Other times it's a real pain and you really don't want to do it. Here, these derivatives don't simplify anymore, so I haven't done any more steps, but sometimes I may do more simplifications for various purposes. Okay, so there are a few examples. There's a whole lot, there's infinitely many examples we can do, but I'll put some more examples like this in the online homework, and then there will also be some rules in the next lecture that we'll learn that will allow us to compute even more kinds of derivatives. And there will be a bonus video showing kind of why this derivative happens to be true. It'll be completely optional. You don't have to watch it, but if you're interested in why this is true, you can go watch that lecture. All right, I'll see you guys in the next one.